Hello friends, I welcome you all on my YouTube channel Rasayan Setu. So friends, in this video, I discuss some questions of coordination chemistry which was asked in TIFR exams. Okay, so basically friends, in this video, I cover the questions coming from the year 2015 to 2020. Okay, so in this video, we cover all the questions coming in from the year 2015 to 2020 TIFR GS exams. Okay, now first of all we discuss a single question which was asked in your TIFR GS 2015 exam. Okay, so let's see the question and see, it says, for cobalt in oxidation state second, predict the overall changes of the coordination complexes shown in the reaction below. Okay friends, so friends, in this question we have a reaction of cobalt complex with HCl and NOH, and we must find the values of X, Y and Z. Okay, and the given condition is cobalt present in second oxidation state. Understand? Okay, so let's do the solution of this question. Now this question is asked in TIFR 2015. Okay, now you clearly see in this question they give you a reaction of the hexa-coordinated cobalt complex with HCl, and it give you this another complex, that is CuCl4 with Y plus 6H2O. Okay, and the another reaction of this cobalt complex is with sodium hydroxide, and we obtained this complex, that is COH2O whole 4 Z. Okay, so this data is given in your question. Now we must find the value of this X, Y and Z. Okay, now first of all, for finding X, that means ultimately you must find the primary valency of this coordination complex. Okay, you know very well that the valency shown on the right hand side corner of this bracket is known as primary valency of that complex. Understand? So it means you must find the primary valencies of all these complexes. Now first of all, for this complex, that is COH2O whole 6X. So in this complex, cobalt is present in +2 oxidation state according to your question. Okay, so for +2 plus 6 multiplied by 0, see the charge present on H2 ligand is 0. H2 is a neutral ligand. Okay, so its contribution will be 0 is equals to X. So there is value of X will be +2. Okay, so here the value of X will be +2. Now in second complex, CuCl4Y, here cobalt present in +2 oxidation state plus there is a negative charge present on chlorine ligand. Okay, so that means it will be 4 multiplied by -1 is equals to Y. So it means +2 minus 4 is equals to Y. So ultimately the Y will be -2. Okay, so the value of Y will be -2. Now in third complex, that is COH2O whole 4 OH twice Z. So in this complex, cobalt present in +2 oxidation state, the H2 is a neutral ligand and OH is also a anionic ligand, so it will be -1. Single negative charge present on OH ligand is equals to Z. So when you solve this equation, the value of Z you get is 0. Okay, so we get values of X, Y, Z respectively are +2, -2 and 0. So X is +2, y is -2 and z is 0. Understand? So according to this result, your option number B is the correct answer for this question. Okay friends, it is again a very simple question friends, which was asked in your TIFR GS 2015 exam. Okay, so now we move towards our next question, and this question is asked in your TIFR GS 2016 exam. Understand? Okay, so let's see this question, and see, it says predict the products of the following reactions. Okay, so we have a two reaction in this and we must find the product X and Y. Understand? Okay, so let's do the solution of this question. Now you see, this question is asked in TIFR 2016. Okay, the first reaction is in between this complex. This ligand is triphenylphosphine plus 2 moles of Cl minus gives X. Okay, and the next one is 2 moles of PPH3 gives Y. Okay, you must find the products X and Y. Now friends, first of all, for solving this question, we have a idea about the geometry of this substrate molecule. You must know the geometry of that substrate molecule, because the solution of this question is depends on this geometry of this question. Now how it depends on the geometry of this question? See, when you observe the geometry of these two complexes, their geometry are square planar geometry. The geometry are square planar geometry for both complexes. That means this complex is present in square planar form, and this complex is also present in square planar form. Now first we talk about the first reaction, that is the reaction between this complex. Okay, now in first step, one chlorine atom attacks on this substrate molecule, and the substitution of one PPH3 group is done by one chlorine atom. Okay, and we obtained this product. Now there is a second chlorine atom also present in this reaction, which is also attacks on this species. Okay, so the second chlorine atom will also attack on this species, friends. Now friends, see, for when this chlorine atom is attack on this in this molecule, there is a two spots on which this chlorine anion attacks. Okay, either it will attack on this position or it will attack on this position. So which position prefer for attack is depends on the trans effect. So here we use the concept of trans effect or trans directing nature of the groups, attached group with central metal atom. Okay, so according to a trans directing series, we know very well that the trans directing nature of triphenylphosphine is greater than chlorine negative ion. Okay, so the trans directing nature of triphenylphosphine is greater than chlorine negative ion. That means in this complex we have two positions for attack of chlorine anion, either this position or this position, but here chlorine preferably attack on this position. This position prefers for attack. Why this position prefers? See, this position is trans to triphenyl phosphine and this position is trans to chlorine, and you know very well that according to trans-directing series, the trans-directing nature of triphenyl phosphine is greater than chlorine atom. Okay, that's why here this position trans to triphenyl phosphine prefer for attack of Cl anion, and the product obtained for this reaction is this. Okay, so this product is obtained by this reaction. Okay, now the geometry of this product is cis geometry. Why cis geometry? You clearly see that both ligands are present on same sides. Here both triphenyl phosphine ligands are this side and both chlorine ligands are on this side. So this type of molecules can known as cis molecules. Okay, so this molecule is a cis in geometry. Okay, now we talk about second reaction. So in second complex, this complex is present PtCl4 2 minus. Okay, now here same mechanism follows. That means first of all the first triphenyl phosphine molecules attacks on this molecule and we obtain this species. Okay, now after that the remaining triphenyl phosphine molecules attacks on this complex. Now see here also it has two positions for attack. Either it will attack on this position or it will attack on this position, and the deciding factor here is also trans effect, and you know very well that trans effect of triphenyl phosphine is greater than chlorine. So now you clearly see that this position prefer for attack. This position is preferred for attack, not this position. Why? Because you see that this position is trans to chlorine, but this position is trans to PPH3, and PPH3 and trans-directing nature of PPH3 is greater than chlorine. That's why this position prefers. So PPH3 is attack on this position, not this. Okay, so ultimately we obtain this product. Okay, we obtained this product. Now you see the geometry of this product is trans. Why we say this is trans geometry? Because you clearly see that this both chlorine ligands are trans to each other and both PPH3 ligands are trans to each other. Okay, so for first reaction we obtain cis product, and for second reaction we obtain trans product. So on the basis of these results you clearly see that your option B is the correct answer for this question. Option B is the correct answer. Okay, see once again the whole solution of this question, friends. So here this question is solved on the basis of your trans-directing nature of the ligands or attached group with metal atoms. Understand? Now we move towards our next question, and this question was asked in TIFR 2017 exam. Okay friends, and see it says given the molecular formula of the hexa coordinated complexes first, second and third, if the number of coordinated NH3 molecules in first, second and third respectively are 6, 5 and 4, then the oxidation state of cobalt in first, second and third are respectively, and we have 4 options. So friends, in this question we have a molecular formula for the coordinated complexes with the coordination number of NH3 molecule, and on the basis of this data you must find the oxidation state of cobalt in these coordinated complexes. Okay, so let's do the solution of this question. So now this question is asked in your TIFR 2017 exam. Understand? Okay. So the molecular formula of first complex will be COCl3 dot NH3 whole 6. Okay, and according to your question, the it is a hexa coordinated complex. First of all complexes first, second and third are hexa coordinated complexes. That means the ligands attached with cobalts are 6 in number. Okay, so hexa coordinated complexes, and according to your question, in first complex the coordinated NH3 molecule is 6. So in this molecule the coordinated NH3 molecule, that means molecules attached with cobalt is 6. So that means their formula is CO NH3 whole 6. Okay, so that means all 3 chlorine atoms are present as a secondary valency. So the primary valency present on this molecule is +3. Okay, and you know very well that we must find the oxidation state of cobalt in all 3 complexes. So first of all, you must find the oxidation state of cobalt in this complex. So in this complex, this NH3 is a neutral ligand, so its contribution will be 0. Okay, so now that means when all ligands present in your coordinated complexes are neutral ligands, that means the valency present on your coordinated complex, that is primary valency, is also known as the valency of that central metal atom. When all coordinated ligands whose attached with central metal atoms are neutral in nature, that means the primary valence of that complex is also a valency of that metal atom. This is a general concept in your coordination chemistry. So that means in this complex the cobalt present in +3 oxidation state. Okay, now we talk about second molecule. So for second molecule, it will be CuCl3 dot NH3 whole 5, and according to your question, the NH3 ligands are attached with cobalt in this second molecule is 5, but it is a hexa coordinated complex. So that means the NH3 attached with cobalt is 5. So that means out of these 3 chlorine atoms, 1 chlorine is attached with cobalt. So now 2 chlorine atoms are present as a secondary valency in this complex. So that means the primary valence of this complex is +2. Remember, this is a valency of complex, not valency of central metal atom. So here you know very well that not all ligands are neutral in nature. Here we have a anionic ligand also, which is contributed in your which is also a deciding factor when you decide oxidation state of metal. So that means here let's assume the oxidation state of cobalt is X plus NH3 is a neutral ligand, means its contribution will be 0 plus 1 chlorine atom present, that means 1 into -1 is equals to +2. So when you solve this equation, you also get the value of X will be +3. Okay, so that means in the second complex cobalt is present in +3 oxidation state. Now we talk about third complex. This third complex is given as COCl3 dot NH3 whole 4, and according to our question, NH3 molecule, NH3 ligands attached with cobalt in this complex is 4. Number of NH3 ligands is 4 in this complex attached with cobalt. So that means the number of NH3 molecule is 4, but it is also a hexa coordinated complex, means out of these 3 chlorine ligands, 2 chlorine ligands are also present in this complex. So one chlorine atom is present in secondary valency. So that means the primary valence of this complex is +1. Okay, but here also it is a primary valency of that complex, not for cobalt. So for cobalt, let's assume its valency is Y plus the 4NH3 is contribution is 0, then 2 for minus 1 is equals to plus 1, because 2 chlorine atoms and 1 chlorine is contributed minus 1. So when you solve this equation, you also get Y is equals to plus 3. Okay. So that means in all three complexes, this cobalt central metal atom are present in plus 3 oxidation state. So the value, so it means according to this result, we say that your option number D is the correct answer for this question. Understand friends? Okay, option D is the correct answer for this question. Okay. Okay, so now we move towards our next question, and this question is also asked in your TIFR 2017 exam. So this is a second question which was asked in TIFR 2017 exam. Okay, the previous one is the first question. This is a second question. Remember. Now the question says the complex showing a spin only magnetic moment of 2.82 Bohr magneton is, and we have four options. So in this question we have four complexes, four coordinated complexes, and you must find that what complex is showing a magnetic moment value is 2.82 Bohr magneton. Okay, so let's do the solution of this question. Now friends, we know very well that for spin only magnetic moment we have a clear formula, that is mu is equals to under root n into n plus 2 Bohr magneton, where n is a number of unpaired electrons present in d orbitals of central metal atom. Okay, n is a number of unpaired electrons present in central metal atom, d orbital of central metal atom. Okay, so on the basis of the calculation of this number of unpaired electrons, you must find the spin only magnetic moment value of that complex. Okay. Now in A option, the complex is NiCO whole 4. Okay. So in this complex, you clearly see that there is no valency there is no primary valency present in this complex. That means here the nickel present in zero oxidation state. So for zero oxidation state, the electronic configuration for nickel is 3d84s2. This is the electronic configuration of nickel zero central metal atom. But you know very well that carbon monoxide is a strong field ligand. So that means in presence of strong field ligand, pairing of electrons occur, or electrons shift from s orbital to inner d orbitals. Okay, in case of strong field ligand, we know very well that shifting of electrons from s orbital to inner d orbital occurs, or pairing of electron also occurs. Okay, so that means here these two electrons from s orbitals can shift from this s orbital to this d orbital. So in the case of octahedral field of CO, in case of octahedral ligand field of CO, the electronic configuration of this nickel metal atom will be 3d10. Now after this, it has one empty s and 3 empty p orbitals which combine with each other, and we have a sp3 hybridized coordinated complex of this NiCO4. So the hybridization of this complex is sp3. Okay, and on the basis of this result, you clearly see that here the value of n, that is number of unpaired electrons, will be 0. So that means for this complex, the spin only magnetic moment is also a 0, because there is a value of n is 0. Understand? So it is not a correct choice for this question. Now we talk about the option number B, that is NiCl whole 4 2 minus. Now in this condition, nickel present in plus 2 oxidation state. Okay, so now nickel present in plus 2 oxidation state, And for nickel plus 2 oxidation state, its electronic configuration is 3d8 4s0 4p0 also. Okay, and chlorine is a weak field ligand, so that means there is no pairing occurs for d electrons. In case of a strong field ligand, there is a pairing occurs, which you see in your first case. Okay, in case of a strong field CO ligand, pairing of this D8 and S2 electrons occur, and electronic configuration of this nickel is 3d10. But here, because of weak field chlorine ligand, there is no pairing occurs. Okay, and it has also empty s and p orbitals, so its hybridization will also sp3 hybridization. Okay, but here it has 8 electrons in d orbital. Nickel plus 2 has 8 electrons in d orbitals, which are filled in this form. Okay, that means in this condition the value of n, that is number of unpaired electrons, are 2. Okay, so that means it has unpaired electron, that means it shows some value of magnetic moments. So its value of magnetic moment will be under root n into n plus 2. So here n is 2, so it means under root 2 into 2 plus 2, that is 4. So 4 into 2 is under root 8, and under root 8 means the value of mu is approximately 2.92 Bohr magneton. Okay, so that means this complex show 2.92 Bohr magneton, which is your option B. So option B is the correct answer for this question. Understand? Now you when you compare option C and D, see, in option C it has also NH3 as a strong field ligand, nickel present in 2 plus oxidation state. Okay, so in presence of strong field, pairing occurs, so these 8 electrons can pair up into 4 d orbitals. So that means in a third complex, value of n will also 0. Similarly, in fourth complex, that is NiCN4 2 minus, Cn is also a strong field ligand. So here pairing also occurs, so here the value of n is also 0. So only and only your option B is a complex in which unpaired electrons are present. So that means it shows some value of the magnetic moment, which is 2.92 Bohr magneton. Understand? Okay. Okay, now we move towards our next question, and this question is asked in your TIFR 2018 exam. Okay, so let's see the question, and see, it says identify the high spin complex amongst the choices given below, and we have 3 choices, 4 1 is none of the above. So out of these 3 choices, you must find the high spin complexes amongst them. Understand? Okay, so let's do the solution of this question. So remember, this question is asked in TIFR 2018 exam. Now we have 3 complexes. The first one is CO NH3 whole 6 3 plus. The B complex is CO CN whole 6 3 minus, and the C complex is CO F6 3 minus. Okay, you must find the high spin complex amongst them. So friends, you know very well that in coordination chemistry, when we talk about a high spin or low spin complex, that means we talk about the contribution of inner or outer d orbitals in formation in hybridization. Okay, when inner d orbitals of central metal atom are used for bond making, for hybridization, that means this complex is inner sphere complex. Okay, or we can say that this type of complex is low spin complex. But when the outer d orbitals of the central metal atoms are used in complex formation, or you can say hybridization, that means in this condition this type of complex are known as high spin complex. Okay, so and what criteria is deciding, what is the deciding factor for this high spin or low spin complexes? So it will be decided on the basis of your ligand field strength. Okay, so when there is a strong field ligand present in your complex, in the presence of a strong field ligand, so the complex will be low spin complex. But in the presence of a weak field ligand, the complex will be high spin complex. That means in the case of strong field ligand, inner d orbitals are used in complex formation, and in case of weak field ligand, outer d orbitals are used in complex formation. Understand? So you must check that what option contain weak field ligand out of these three options. So you clearly see that option number C is contain weak field ligand, that is fluorine, or NH3 is a strong field ligand. Only option number C contains weak field ligand, that is COF6 3-. Okay, so that means this complex is a high spin complex. So your option C is the correct answer for this question, that is COF6 3-. Okay, because it contains weak field ligand. Okay, I hope you understand it. Now we move towards our next question, and this question is asked in TIFR 2019 exam. Okay, and see, it says in isoelectronic series, given this series, okay, all members have intense charge transfer transition. The incorrect statement is, and we have four statements. So friends, in this question we have a isoelectronic series of these three complexes, okay, and they show intense charge transfer transition. So you must find the incorrect statement for their charge transfer transition out of these four options. Understand? Okay, so let's do the solution of this question. Now you remember this question is asked in TIFR 2019 exam. So in this question we have this isoelectronic series. Okay, so this is a complex of vanadium, this is a chromium, this is manganese. So first of all you must find the oxidation state of metal ion these complexes. So in this complex the oxidation state of vanadium is 5 plus. In this ion the oxidation state of chromium is 6 plus, and in this ion the oxidation state of manganese is 7 plus. Now on the basis of this oxidation states we clearly say that their electronic configuration is 3d0 and 3d0. That's why these are known as isoelectronic species, first of all, okay, because their electronic configuration will be same, the number of electrons are same in these complexes, that's why they are isoelectronic to each other. So that means there is a common thing or similarity in these three complexes. What is similarity? That these all complexes containing empty d orbitals. All three complexes are contains empty d orbitals and filled orbitals of oxygen ligand also. So all species contains empty d orbital of metal ion and filled orbital of oxygen ligand. Okay, this is a common thing present in these complexes. Now you we know very well that in coordination chemistry, when in a coordinated complex, a complex contains empty d orbital and a filled metal and a filled ligand orbitals, there is a possible electronic transition from the filled orbitals of ligand to empty orbitals of metal ion. In this condition, an electronic transition occurs between filled orbitals of ligands and empty d orbitals of metal ion, and this type of transition is known as ligand to metal charge transition, ligand to metal charge transfer spectra. Okay, so simply in all these complexes we have a ligand to metal charge transfer spectra. So they all complexes show ligand to metal intense charge transfer spectra, because in this species we have filled ligand orbitals and empty metal orbitals. So there is a transfer of charge from the filled ligand orbitals to empty d orbitals of metal atom, and this is responsible for their intense color also. So this is responsible for intense color. Ligand to metal charge transfer spectra is also responsible for intense color of the complexes. Okay, so that means on the basis of this point, your point number A is the correct statement, which states that, see, charge transfer transitions are attributed to excitation of electrons from ligand to metal. So in this complex, charge transfer transition occurs because of excitation of electron from ligand to metal. So here this is a, suppose this is a high energy metal orbitals and there is a low energy ligand orbitals. So there is a charge transfer occurs between this filled ligand to empty metal orbital. Okay, so that means your A statement is correct. So this is not an answer, you must choose the incorrect statements. Okay, now friends, in ligand to metal charge transfer spectra, we clearly know that there is an energy gap present in between the empty orbitals of metal atom and filled orbitals of ligand. Okay, so this is, suppose this is a energy gap is present in between filled empty metal orbitals and filled ligand orbitals. Okay, so there is an energy gap present in between these orbitals, and now we know that this energy gap is depends on electronegativity of ligand and metal. Okay, so this energy gap, friends, remember this is an important concept, listen carefully. Okay, this energy gap is depends on electronegativity, is depends on electronegativity of ligands and metal, ligands and metal, this energy gap. Now how can we relate the electronegativity with oxidation state? Okay, so now we relate the electronegativity with oxidation state. See that when oxidation state of metal increase, its electronegativity will also increase. Remember, this is another important concept. When oxidation state of metal increase, its electronegativity will also increase, electronegativity of metal. And when, and how can you relate the energy energy of that metal with electronegativity? So when electronegativity increase, its energy will decrease. We talk about energy of metal orbital. First of all, we talk about energy gap. Now we talk about the relationship between oxidation state of metal and its electronegativity, and now we relate this electronegativity with this energy level of the empty orbital of this metal. So when electronegativity of metal increase, its energy will decrease. Remember, when electronegativity increase, its energy decrease, and when energy decrease means this energy decrease, that means this gap will also decrease. When oxidation state of metal increase, its oxidation is electronegativity increase, and when electronegativity increase, its energy decrease, and when energy of metal decrease, that means the gap between the orbital of this metal and this ligand will also decrease. This is the energy gap. That means it will shift from higher energy region to lower energy region when oxidation state increase. Okay, when oxidation state increase, its in energy decrease. So that means energy gap between metal and ligand decrease. This is a sign of decrease, this is a sign of increase. Okay, means energy gap between metal and ligand decrease. And now we talk about the wavelength of this energy transition, this transition. Now wavelength is inversely related to your energy, required energy, from the relationship E is equals to hc upon lambda. There is an inverse relation between wavelength and energy. So when energy gap decrease, that means energy decrease. So required energy decrease means wavelength of this transition increase. Wavelength of this related to this transition is increase. So that means here this complete concept we use for solving this question. This is an important concept, friends. Okay. Now see once again, when energy gap is depends on electronegativity of ligands and metal. Now oxidation state increase means its electronegativity increase, means its energy decrease, and when energy decrease means this energy gap will also decrease, and when this energy gap is decreased, that means its wavelength increase. So now when you compare the energy gap of this species, of this given species, so that means it is V5 Cr6 plus and Mn7 plus. So this is the highest oxidation is present in manganese 7 plus, and we know when oxidation state increase, the energy gap between metal and ligand decrease. So the complex containing highest oxidation state metal have least energy gap between the orbitals of metal and ligands. So when we draw a tentatively energy gap diagram between the orbitals of metal and ligands for these complexes, we clearly draw this diagram. See, on the basis of above concept, the largest gap is present in between the orbitals of vanadium and oxygen, because it is least in oxidation state. Now the second one is in between chromium and oxygen, and now least energy gap is present in between your manganese and oxygen. Okay, here we also use same concept. When oxidation state increase, its electronegativity increase, and when electronegativity increase, energy decrease, and when energy decrease means this energy gap between metal and ligand will also decrease. So this energy gap decrease, and when this energy gap decrease, the wavelength increase. Okay, so that means what is a wavelength order in this energy transition? So the highest wavelength for MnO4 minus, then for CrO4 2 minus, and then for VO4 3 minus. So this is a wavelength order for this charge transfer transitions. Okay, wavelength order. Understand? Now friends, on the basis of this, you clearly see that your D point is also a correct statement, which states that, see, the change on the metal of nucleus increase in the order. See, this is a change of the change on charge, sorry, not change, this is a charge. So charge on the metal nucleus increase. See, the least charge is present in vanadium, then chromium, then highest charge present in manganese. Okay, so this statement is also a correct statement. Now according to your statement C, it is also a correct statement, which states that the wavelength of transitions increase in the order. See, this is the decrease order of wavelength of transition, or reverse of this is an increase order of the wavelength of transitions. Okay, so that means option C is also a correct statement. Now that means your option B is the correct answer for this question, which is an incorrect statement for these complexes, which states that MnO4 minus exhibits charge transfer at shortest wavelength, but not MnO4 exhibits charge transfer at longest wavelength. This charge transfer is least in energy but have longest wavelength. Okay, so option B is the incorrect statement for this question. Understand? Okay, now see once again the whole solution of this question, friends. This is an important concept. Remember this concept. On the basis of this concept, you clearly solve the solution of this question. Okay. Okay, now we move towards our next question, and this question is asked in your TIFR 2020 exam. Okay, and see, it says a complex of chromium 3 plus in aqueous HCl was found to exist in two geometrical isomeric forms. A white PPT was formed on addition of equimolar amount of silver nitrate solution to the complex. The structure of the complex is, and we have four options, that is A, B, C and D. So friends, you must find that what option show geometrical isomerism simply. Ignore all the other points, that is aqueous HCl, or you can say white PPT was formed, addition of equimolar amount of silver nitrate, etc, etc. You must clearly focus only and only single point, that is geometrical isomerism. Okay, so you must only find the which compound show geometrical isomerism out of these four compounds. Okay, so let's do the solution of this question. So remember, this question is asked in TIFR 2020 exam. So in coordination chemistry, we know very well that in case of octahedral complex, the complex type with Ma2B4 show geometrical isomers, that is cis and trans. This cis and trans isomers depends on the position of the two identical ligands. Okay, when two identical ligands are present adjacent to each other, that means they are cis to each other, and when two identical isomers are situated opposite to each other, that means they are trans to each other. So you must compare this formula with all these options, and those options which can match with this formula is a geometrical isomer, which it show geometrical isomerism. Okay, so when you carefully observe all these options, we clearly see that the option B is a match with this formula. That means here the M is Cr, the A2 is Cl2 and the B4 is H2O4. Okay, so only option B shows geometrical isomerism. So option B is the correct answer for this question. Okay, option B is the correct answer for this question. Now we can draw the geometrical isomers of this complex. See, option B is this CrCl2 H2O4. The first form is cis form and the second form is trans form. So first we draw a cis form of this complex. See, for cis form, I say that two identical ligands are adjacent to each other. or the bond angle between two identical ligands is 90 degree. So it means here two identical ligands are chlorine ligands, so they are identical, chlorine and chlorine, and you clearly see that the bond angle between this chlorine and chlorine are 90 degree. Okay, and these are 4H2O present. So this is cis form of this complex. Now we draw transform, and for transform I say that two identical ligands are present opposite to each other, or you can say that the bond angle between two identical ligands is 180 degree. Okay, so here two identical ligands are Cl, so this Cl and this Cl present in opposite to each other, that means their bond angle is 180 degree, and rest H2O ligands are situated in this form. So here chlorine and chlorine are opposite to each other, so it is a transform. So option D shows geometrical isomerism, cis and trans isomerism. Okay, understand? ओके, सो नाउ फ्रेंड्स ये थे आपके कुछ कोऑर्डिनेशन केमिस्ट्री टॉपिक के क्वेश्चंस जो आपके प्रीवियस ईयर टिफर एग्जाम्स में पूछे गए थे. इस वीडियो में मैंने आपके 2015 से लेकर 2020 तक के टिफर एग्ज़ाम में कोऑर्डिनेशन केमिस्ट्री के क्वेश्चंस को कवर किया है. फिर भी इसके अलावा अगर आपको कोई प्रॉब्लम आती है किसी भी कॉन्सेप्ट को समझने में, कहीं भी किसी क्वेश्चन में, तो प्लीज़ आप कमेंट सेक्शन में आके ज़रूर पूछिए. ओके, so now thank you friends, and thank you for watching.